So in this one we want to rank acids by pKa. It's a sampling question. So of course we need to know what pKa means. A low pKa means it's more acidic or less acidic? More acidic, right? Low pKa means more acidic. So the first thing, they give you things drawn out with like CH3, CH2. You need to turn that into a line bond drawing. First thing you need to do is take all those things that look like this. And you need to turn that into this right away. That'd be the first thing. So once you do that, it becomes a lot clearer what's going on here, right? Seeing it like this maybe is tougher. It doesn't quite make, you can't see it as well. Draw it as these line bond drawings. So if you see all of these are what kind of functional group? They're all carboxylic acids. So we're talking about, when we talk about the reactivity of these acids, we're talking about the reactivity of this OH bond in all these cases. That's the most polar bond to hydrogen. And what's different about these? It looks like you're adding chlorines. Right? So one chlorine, two chlorines. And the position they're at, how far away they are from that OH bond. Right? So remember, this is that induction principle, right? About something electronegative pulling electrons, right? Making this more delta plus. So the closer this is, the more it can affect it. And the more of them, the more that effect will be. So I would rank these. This would have the lowest pKa, so I'll put this as 1. This would be 2 because it's closer, 3, and then 4. So the lowest pKa will be the one with 2 chlorines, 1 carbon away. Then one chlorine, 1 carbon away. 1 chlorine, 2 carbons away, and then no chlorines. E and Z alkenes. So what you're responsible for knowing right now is essentially, right, the difference between E and Z. So Z means Z same side. So the highest priority groups are on the same side. So if you were to split the alkene down the middle, right, this is a CH3, even though it's not drawn in that way. This is a CH3. Both the highest priority things, right, carbon versus hydrogen, carbon takes priority. Hydrogen versus carbon, carbon takes priority. They're on the same side. We call that a Z alkene. Versus when the highest priority things are on opposite sides. So if you split the alkene down the middle, this carbon, the highest priority thing's over there. Highest priority thing's over here. So we call this an E alkene. We do not use E and Z with anything else. They're only used with alkenes. So you can't say a cyclohexane is E or Z. It's cis or things are cis or trans on that. So this only has to do with alkenes. All right, so a question that says, add curved arrows to the reactants to indicate the movement of electrons in this reaction. So just taking a look here, there's a couple things you always want to do first. Identify the nucleophile and identify the electrophile. Right? So where is the nucleophile? We're only talking about the starting materials. They're giving you the products. Which one is the nucleophile? Where is it electron rich at? Or which one's the electrophile? Where is it electron deficient at? H is what? Which H? The HCl-H, right? The hydrogen bonded to chlorine. I would agree. We're going to call that delta plus. That's the electrophile. That hydrogen is the electrophile. All right, so what's the nucleophile then? Where's it electron rich at? What part of the nitrogen? The lone pairs, even better. So my arrow is going to start there. All right? And it's going to go towards the hydrogen. Now, how do I know that? Because if I looked from my starting materials to my products, what new bonds were formed? What new bond was formed here? An NH bond. What kind of NH bond? A sigma NH bond. So I know I need to show arrows to make that bond. Right? What bond was broken from starting material to products? A sigma HCl bond. So I know I need to show arrows to make sure that I break that bond. So I need to show these arrows, those electrons go into that chlorine now. Because also, look, the chlorine in the product has an extra lone pair, doesn't it? Where is it getting that lone pair from? It's getting it from this bond. How many electrons in a bond? 2. Be careful. What I see a lot of times is what people will do is they want to show like, you'll never do arrows over this arrow. you only have two starting materials react. Never have your arrows come over and try to react with a product, right? Also, arrows never kind of loop back. They always kind of flow, right? Just like in resonance, they kind of go one direction. They never come looping back around. Not yet, at least. They don't come looping back around. Notice how they all kind of went this way? Good. Just showing an example we had the other day. An alkyne, a terminal alkyne, CH, SP hybridized. Make sure we have our lone pairs all drawn in, right? Nitrogen with a negative charge, 2 lone pairs. That's going to be our nucleophile. This hydrogen is going to be our electrophile. What bond did we form? We formed a new sigma NH bond. Which bond did we break? A sigma bond between carbon and hydrogen. So we know we need to show arrows to indicate that happening. The nitrogen that forms that new NH bond. At the same time as that NH bond is formed, the 2 electrons in that carbon-hydrogen sigma bond, that breaks. Those 2 electrons end up right here. The new NH bond is right here. That's the mechanism. So be careful, right? If I show you this, I show you the starting material, I show you the products, you got to draw the mechanism to make those products. Done. I'm not asking you to think about anything else. All I want you to do is show me arrows to make these products. Yep, I'm not asking you to predict products yet. Recording? Shoot. So in this reaction, similar to the one we just did, we need to form a sigma NH bond. We need to break a sigma CH bond. The nitrogen's the nucleophile. The hydrogen's the electrophile. We show an arrow to show the formation of the new NH bond. It's right there. And we show an arrow to show the breakage of the CH bond right there. Now the second part of this is what kind of arrow do we have here? So one example of the arrows they show is this kind of arrow. What kind of arrow is that? It's a resonance arrow. Are we doing resonance? No. So this is not the right arrow. Right? Remember, resonance arrows are different than reaction arrows. I showed you this is a resonance arrow. So this is not the right answer. Resonance arrow. So that's not right. All the other arrows are equilibrium arrows. Right? They're equilibrium arrows. Which way do you think this equilibrium lies? Towards the left or towards the right? Does it lie towards the starting materials or towards the products? Probably the left. Why? Not even knowing any basic chemistry stuff. Why would it lie this way versus this way? Less charge. Right? Would you think these are more stable or less stable? These things on the products, are they stable or unstable? Unstable. So which way do equilibriums lie? They lie towards stable stuff. Right? So this arrow that should be here should probably have a bigger part going back towards the left, towards the starting materials, and a smaller arrow going towards the right. So I think that would be C in this case. Or B in this case, sorry. Right, the arrow going more towards the starting materials, less towards the products. Because of stability, which we talked about, right? This is the kind of stuff we talked about a little bit. So 4 reaction types. The first type reaction you learned was substitution. And that's just one group being substituted for another. So one example could be, right? In this case, the iodine has been substituted for an OH group. That's a substitution reaction. Another type of reaction is an elimination reaction. I could take the same exact starting materials, and the only difference will be here, instead of doing a substitution, I'm doing an elimination. So that means I will form a pi bond. All right. So what I did here was an elimination reaction. Right? What happened? I took a hydrogen from here, right? Lost 2 things, eliminated 2 things. What did I eliminate? I eliminated a hydrogen and an iodine. I ended up with a water and sodium iodide and a pi bond elimination reaction. Sorry. So third kind, addition. You start with a pi bond, and we end up with 2 things being added. So what do we add here? We added the bromine, and then of course I didn't draw it in because I'm an organic chemist and I'm lazy. This carbon had 2 hydrogens. Now this carbon has 3. So I got both an H and a Br adding across that pi bond. That's an addition reaction. Trying to think of a good one for you guys. These are a little more complicated. Example of rearrangement. So example of rearrangement would be, right? Rearrangement means you don't change the molecular formula. All that's you're not adding anything, you're not eliminating anything, you're not substituting anything. All you're doing is changing the constitution or the constitution of an atom, or its or changing the type of isomer it is. So the first example you saw in class was we went from an E to Z alkene. And another way could be if you had things trans, and then somehow they became cis. That would be a rearrangement, a spatial rearrangement. That would be kind of a rearrangement reaction. Right? Rearrangements, molecular formula stays the same. You're not adding anything. You're not taking anything away. You're not substituting anything. You're just moving things around, either changing the constitution, the bonds, or the 3-dimensional space. So be really, really careful. Rearrangement is not resonance. Resonance is the same molecule. You're just moving electrons around. A rearrangement, either you literally you break bonds, or you change conformation or isomer. You either go from a cis to trans, E to Z. Resonance, you're just moving electrons around. Good. So let's see if we can take a wedge and hatch structure and turn it into a Fischer projection. Right? We didn't practice this too much. It'd be kind of tough. I'm going to draw in the H's here because they're implied. I'm going to draw out my Fischer projection. So if I number these carbons, that's one good thing you want to do is number the carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right, so the Fischer projection, I want to have that backbone drawn out. So it's 1, 2, 3, 4, 5. Carbon 3 is pretty easy. What's on carbon 3? Just, I don't have to worry about what side they're on. Right? So if my eye is looking down this way, right, what do I see? The OH is coming out at us. These I look maybe like my left-hand side. This OH would be over here. That H would be here on carbon 2. Also, even if you drew it maybe a little different, this OH and this OH, are they on the same side or opposite sides? OH and OH are on the wedge and wedge. The OH and the OH are on the same side. Thank you. You're going to get it eventually. So that means they'd be next to each other, and that'd be there. And that's how you draw it as a, right? But remember Fischers, then to take it back, Fischers are a little strange because the things on the horizontal axis are coming at you, and the vertical are going away from you. Right? That's how Fischer projection looks.